Good morning. My name is Ravimba Koranjai, and today I will present our work on Smartify, a unified multi-agent AI framework for automated vulnerability repair in smart contracts written in Solidity and Move. Our motivation for this work is the growing reliance on smart contracts as critical infrastructure in decentralized finance and beyond, and the reality that bugs in these contracts can directly translate into large, irreversible financial losses. In this talk, I will first show the scale of the security problem, then discuss why existing analysis and LLM-based approaches are insufficient, introduce the Smartify multi-agent architecture, and finally present a cross-language empirical evaluation on both Solidity and Move. Our key message is that a role-specialized, human-inspired agentic system can significantly improve both the accuracy and reliability of LLM-based vulnerability repair compared to the monolithic purely chain-of-thought models. Over the past few years, financial losses due to smart contract vulnerabilities have reached the multi-billion-dollar range, and this is not a theoretical concern anymore, but a recurring operational reality for the DeFi ecosystem. By 2023, cumulative losses from attacks against Ethereum smart contracts alone exceeded 3.1 billion US dollars. And if we look at the broader DeFi ecosystem, the estimated total stolen due to vulnerabilities is around $9.04 billion. High-profile incidents such as the DAO hack with roughly $55 million lost and the Polynetwork incident with almost $600 million stolen illustrate how a single contract bug can have ecosystem-wide consequences. The figures on this slide summarizes how these losses have escalated from around 0.5 billion in 2020 to over 9 billion in 2023, showing both the growth of DeFi and the growing attack surface. Compounding this, smart contracts are immutable once deployed, so a vulnerability is not just a bug to be patched later, but a permanent on-chain liability that can be exploited as long as funds remain locked in the contract. That motivates the central question behind our work. Can we use AI, and specifically LLMs, not just to detect but to reliably repair these vulnerabilities before they are exploited in the wild? Now, traditional static analysis tools such as Mithril and Slither have been very useful for uncovering known vulnerability patterns, but they tend to focus on relatively fixed rule sets and can generate high false positive rates on complex real-world contracts. Dynamic analysis and formal verification tools like Manticore, Ecdina, KVM, and DeepSea provide a stronger guarantees but are often expensive to apply at scale and can struggle with full semantic complexity and size of modern DeFi code bases. More recently, LLMs such as GPT-4 or Claude have been used directly on smart contract codes, but in a monolithic setup, they are prone to hallucination, explanation, and patches, and they provide no formal guarantees about security or exploit mitigation. Manual security audits, while insanely costly by expert firms, still remain the gold standard, but they are expensive, time-consuming, and fundamentally do not scale to the volume of contracts and the velocity of deployments we have seen on the public blockchain. So overall, existing approaches tend to trade off scalability, precision, and trustworthiness, which leads us to look for a new approach that can be accurate, scalable, and at least systematically more trustworthy than a single opaque LLM call. So our architecture, as we want to say, is human-inspired. Here we propose an architecture that explicitly models how a security audit team would collaborate to repair a vulnerability in a smart contract. Instead of relying on a single LLM to do everything in one longer prompt, we decompose the workflow into dedicated roles as an auditor, architect, code generator, and a refiner. The auditor first scans a vulnerable Solidity or Move contract and produces a detailed vulnerability report, which is then consumed by the architect that designs a high-level repair plan but does not write the code. The code generator takes this plan and, with the help of a language-specific retrieval augmented generation component for Solidity and Move, synthesizes the candidate repair patches that follow established best practices. Next, the refiner iteratively improves the code quality, readability, and efficiency. Finally, the validator re-audits the patch contract to ensure that all previously identified vulnerabilities are resolved and that no issue have been reintroduced. This loop can iterate until the validator is satisfied, giving us structured, delegative, and iterative workflow rather than a single linear chain of thought. Now, there are some nuances of this architecture. This looks very simple. However, each of these parts, each of these agents are not based on a single LLM. Each of them has fine-tuned on a very specific task. We will get into that later in the slides. Also, just as a note, these RAG systems do not contain any vulnerable code or vulnerability at all. Their whole reason of existence is to guide the generator to the nuances of if it is a Solidity code or if it is a Move code, and if it is a Move code, is it a SUI blockchain based or Aptos? Now, coming to the specialized agent team. The auditor agent is based on a fine-tuned Gemma 2 9 billion parameter model that has been trained on Solidity and Move code, associated documentation and vulnerability examples, and further aligned with a safety classifier adapted from Google's Responsible AI toolkit. This safety alignment lets the auditor enforce language-specific rules. For example, it ensures that the generated Move code respects the conventions of a particular chain, like Aptos or SUI, and that Solidity code avoids known dangerous patterns. Why this is important? Because Move, even though Aptos and SUI both use Move, they're not exactly compatible with each other. Imagine that as Python 2 and 3. They are the same, based on the same language, which Move itself is based on Rust, but they're not cross-compilable. Now, the architect reads the auditor's report and constructs a strategic repair blueprint that specifies what needs to be refactored or rewritten, such as applying check effects interaction, tightening access control, or restructuring unsafe patterns. But it does not deliberately emit code. The code generator is built on a fine-tuned CodeGemma model, a base model, and uses the separate RAG data stores for Solidity and Move to retrieve relevant best practice snippets and documentation that guide its patch generation. The refiner uses the same CodeGemma backbone, but is now prompted as a critic that repeatedly improves the generated patch in terms of style, maintainability, and potentially remaining weakness. This CodeGemma is not the base model. This has been fine-tuned on an instruction tool model so that it can understand what's going to be improved and potentially work. Finally, the validator reuses the audited model to rescan the repaired contract and verify that all reported vulnerabilities are eliminated and that no unsafe constructs have been newly introduced, closing the loop with a final security check. Now, coming to the evaluation. To evaluate Smartify rigorously, we designed a multifaceted experimental setup that covers both Solidity and Move, and measures not only syntactic correctness but also exploit mitigation and semantic preservedness. For Solidity, we use the not-so-smart contract GitHub repository curated by Trail of Bits, which contains 60 intentionally vulnerable contracts spanning 8 vulnerability categories, including reentrancy, integer overflow and underflow, denial of service, access control issues, and more. For Move, we construct a dataset of 92 real-world projects with 652 modules drawn from major platforms like Aptos, SUI, and Starcoin, covering application domains such as DeFi, tokens, bridges, and infrastructure, building on the dataset used by Song et al. In their paper. We compare Smartify against 15 state-of-the-art code models and general-purpose LLMs including GPT-4, Llama 3.3, CodeGemma, DeepSeek, StarCoder 2, and others, as well as specialized static tools for Move, such as MoveProver, MoveLint, and MoveScan. Our experiments were run training on 4 NVIDIA A100 GPUs and inference on a RTX 4090. And we report matrices like pass at 1, a number of vulnerability fixed, exploit mitigation rate, and inference time to capture both accuracy and practical deployability. To understand where the gains come from, we also perform an ablation study that removes component one by one to see where we are actually gaining it from. So coming to the performance, among the standard code analysis models, CodeGemma achieves strong performance with 16 vulnerabilities and relatively low inference time of 96.5, indicating a solid understanding of Solidity security patterns. So In this slide, surprisingly, you will see for Solidity, CodeGemma performs as well as our model. Now, our Smartify configuration that combines CodeGemma and Gemma 2 matches the top performance, but also it fixes the 16 vulnerabilities with a slightly higher average time due to the extra agentic step and validation. Interestingly, when we wrap a non-fine-tuned general-purpose model like Llama 3.1 inside Smartify framework, we see a substantial boost compared to running the model separately, approaching the performance of much larger models like Llama 3.3 70 billion parameter, but at far lower computational cost. On the other hand, some of the things which surprised us is some specialized code models such as StarCoder 2 and even larger models like DeepSeek Coder 33 billion parameter or CodeGemma performs surprisingly poorly on this repair task, fixing only a handful of vulnerabilities or none at all, which suggests us that pre-training on code alone is not sufficient for robust vulnerability repair. Now, where Smartify really shines is on Move, which is a relatively new security-focused smart contract language with far less publicly training data than Solidity. So most of the LLMs did not have this in enough quantity in their pre-training dataset. Here, we focus on 4 representative vulnerability types in Move: unchecked returns, unused constants, overflow, and precision loss, and report how many instances each model can successfully repair along with the inference time. Now, traditional code models like CodeGemma or Gemma 2 27 billion parameter can repair on the order of tens of issues across these categories, where Smartify with Gemma 2 plus CodeGemma repairs an order of magnitude more, with 650 total fixes reported in our tests. Equally important, Smartify achieves these gains while being about 6.6 times faster than a very large baseline like Llama 3.3 70 billion parameter model, which means it is more practical for real-time or on-device scenarios. We also contrast Smartify with specialized tools like MoveProver, MoveLead, MoveScan, which are strong at detecting vulnerabilities but are not designed to generate repairs. So Smartify complements them by providing repair suggestions that can be validated by these tools. Also, one thing to note is that Smartify works on source codes, whereas most of the other static analysis tools works on the compiled code. Now, these results highlight that our tool actually works and it works better for low resource languages. Now, coming to our ablation study, to understand why Smartify works, we conducted an ablation that compares the full system against variants with no refinement, no RAG, and a single agent chain of thought baseline. Now, this shows that removing the refinement loop causes a noticeable decrease, especially in exploit mitigation rate, indicating that the refiner and validator stages are catching subtle issues that the first pass generator misses. Eliminating RAG has an even stronger impact on Move, whereas pass 1 drops from about 48.9% to 28.3%, underscoring how important in context language-specific examples are for low resources and smart contract languages. The single agent baseline, which asks one Gemma 2 model to do auditing, planning, and repair in a single complex prompt, performs worst overall, particularly on exploit mitigation, suggesting that the role-based delegative architecture is more effective than a monolithic chain of thought approach for this domain. In summary, we can say that the gains we observed are not just from more compute or a better base model, they arise from our very specific multi-agent decomposition, the iterative refinement, and RAG working together as a coherent system. To make this more concrete, we just wanted to give an example. So in this vulnerable version, the contract first performs an external call where message.sender.call and only then updates the internal balance, which violates the check effects interaction pattern and allows a malicious contract to re-enter and drain funds, which is pretty bad. Smartify's patch reorders the operation to follow check effects interactions by subtracting the balance before making the external call, and it wraps the call in a check pattern that requires the call to succeed, returning a Boolean success flag. This example illustrates how the auditor can flag a critical pattern like reentrancy, and the architect can plan to enforce check effect interactions. The code generator can implement the fix, and the validator can confirm the reentrancy conditions is no longer present. Although this is a very simple example, the same workflow extends to more complex vulnerabilities and to Move models. where the framework can reason about language-specific safety properties. Thank you. We conclude that Smartify demonstrates very unified multi-agent framework and significantly improve the reliability and coverage of LLM-based vulnerabilities across both Solidity and Move. In future, we plan to extend this architecture to additional smart contract languages, integrate it more tightly with formal verification pipeline, and explore its use for tasks such as context-aware generation. Thank you.